In this video, we shall discuss linear programming, the Simplex method. We are now dealing with linear programming problems, that is, both the objective function and the constraints are linear. We used graphical method to solve the problem when we have two variables. The optimum solution appears at the corner point or the vertex of the feasible region. To extract all vertices, we can pick any two equations associated to the constraints and solve the simultaneous equations. For example, if we are given this linear programming problem with two variables, we get four equations, each associated to one constraint. Let's ignore the graph for the moment. By picking any two equations from these four equations and solve them simultaneously, we get all vertices. Here, altogether we have 6 vertices. This number of vertices comes from the fact that we choose 2 equations out of 4 equations for each simultaneous system. Therefore, by binomial coefficient, we have a total of 4 choose 2, that is 6 simultaneous equations to solve for. If the 2 equations are not parallel, we obtain one vertex. In our situation, since none of the equations are parallel to each other, so we will get a total of 6 vertices in this linear programming problem. For each vertex, we can substitute back to the other two constraints to see if it fulfills them. If yes, then this vertex belongs to the feasible region. Here, the vertices 0, 0, 3, 0, 0, 3, and 2, 2 are in the feasible region, but the points 0, 6 and 6, 0 are not. Then, by comparing the output value of those vertices in the feasible region in the objective function, we obtain the optimal solution. Even though when we have more than 2 variables in our linear programming problem, we notice that the optimal solution still occurs at the vertex of the feasible region. Therefore, although we cannot use graphical methods to solve problems with more than 2 variables, intuitively, we could still be able to use this idea to solve our problem. That is, we can first extract all vertices by picking several constraint equations to form different simultaneous equations. Then we identify which vertices belongs to the feasible region and compare their output values for the objective function. For instance, if we have the following linear programming problem with 3 variables, we can write 7 equations associated with those constraints. Each equation represents a plane in this situation. We need 3 equations to obtain one vertex. For example, if we solve for this system, we get the point 0, 0, negative 1. How many systems are there? It is the number of ways of choosing 3 equations out of 7 equations. That is, by the binomial coefficient, 7 choose 3, which is 35. It may happen that there is no solution for a particular system, which happens when some planes are parallel. So at most, we get 35 vertices. Among these vertices, we check whether they belong to feasible region, and if yes, we compare their output values and identify the optimal solution. It sounds time-consuming. We can imagine that if we have a linear programming problem with 15 equations associated to the constraints and 6 variables, then the total number of systems to solve for vertices becomes 15 choose 6, which is 5005. With just a little increase in the number of equations and variables, the work involved becomes huge. Fortunately, the Simplex method is a much more efficient way of solving linear programming problems. The idea is that we start at a feasible vertex, and the method moves on to another adjacent vertex with an improvement on the function output, and we continue until it reaches the vertex, which gives the optimal output for your objective function. Then the mechanism stops. The basic tool involved for the Simplex method is Gaussian reduction. We can refer to the figure here as an illustration.